By now, you should be familiar with how a binomial probability distribution works. Performing a coin toss for several independent trials N with two possible outcomes per trial, a success or K or a failure, with a probability of getting a success P and the probability of getting a failure Q being constant in every trial. The two possible outcomes, success or failure, are also discrete in nature. So the Poisson probability distribution is another discrete probability distribution that shares many similarities with that of the binomial probability distribution. Let's look at these examples on Poisson distribution. So consider the distribution of number of deaths attributed to typhoid fever over a long period of time, for example, 1 year. Assuming the probability of a new death from typhoid fever in any one day is very small, okay, take note of that, and the number of cases reported in any two distinct periods of time are independent random variables, then the number of deaths over a 1-year period will follow a Poisson distribution. Okay, so you already have some giveaway clues here as to what a Poisson distribution might be like. The very small chance, okay, or probability of getting a success. So take note, success is not always a positive thing. Okay, in this example, success is a death from typhoid fever. In this case, it's very small probability. So the preceding example concerns a rare event occurring over time. So rare events can also be considered not only over time but also on a surface area, such as the distribution of number of bacterial colonies growing on an agar plate. So suppose here we have a 100 square centimeter agar plate. We assume that the probability of finding any bacterial colonies at any small area around a point A, so let's say this is your point A, okay, and then you have a small area around point A. The probability is very small, so there's that term again, probability is very small, and proportional to the area. So meaning to say, as you increase the area, your probability of finding a colony increases. Okay, as we increase the area, the probability again increases. Okay, so these particular scenarios show us what a Poisson distribution describes. Rare events over time and maybe over surface area, as this example shows. So let's go back to our first example on the deaths attributed to typhoid fever over a year. What is the distribution of the number of deaths caused by typhoid fever from time 0 to time t, where t is some long period of time, such as 1 year or even 20 years? Okay? We can have three assumptions. Okay? So, consider any general small subinterval of time period t denoted by delta t. Okay? So meaning to say your longer period of time, 1 year or 20 years, are subdivided into shorter time periods or delta t's. Okay? Perhaps maybe per week or per month or even per day. So, given that, we can say that the probability of observing one death is directly proportional to the length of the time interval delta t, right? Okay? Of course, it's logical. The longer you wait, the more deaths you might witness, right? Okay? So that is the probability of one death is equal to lambda delta t for some constant lambda. So lambda here is a constant. Okay? Next, we can say that the probability of observing 0 deaths over delta t is approximately 1 minus lambda delta t, meaning to say it's the opposite of this, the probability of observing 1 death. Because this is observing 0 deaths, meaning to say they are complementary events. Right? That's why we have here a 1 minus lambda delta t. Next, the probability of observing more than 1 death over this time interval is essentially 0. So meaning to say, this is a really, really rare event. And the time interval is short enough so that you won't observe more than 1 success or 1 death in this case in this short time interval. Thus, we have this equation of the probability of observing 1 death in a time interval delta t. 2 assumptions are to be observed for this to be true. Okay? The first is the assumption of stationarity. Okay? So here we assume that the number of deaths per unit time is the same throughout the entire time interval t. Thus, an increase in the incidence of the disease as time goes on within the period t would violate this assumption. So it's like constant, okay, constant deaths for a particular time interval t. Note that t should not be overly long because this assumption is less likely to hold true if your time interval increases. Okay? So as your time interval increases, the probability of getting a constant success will be lower and lower. Okay? Meaning to say that successes will tend to increase. Okay? Instead of being constant. Another assumption is this. The assumption of independence. If a death occurs within one time sub-interval, then it has no bearing on the probability of death in the next time sub-interval. Okay, so you might recall your coin toss experiment here, where the first coin toss, the result of that does not really affect the probability of a success or a failure for your next coin toss. So this is the probability mass function of a Poisson probability distribution. Okay? So the Poisson distribution depends on a single parameter, mu. Okay? Remember, your mu here is your expected value. Right? And your mu is equal to the constant lambda times time. The parameter lambda represents the expected number of events per unit time. Okay? So, therefore, the total expected value will be that times the total time. That's what we see here. The parameter mu represents the expected number of events over time period t, or in case of area, A. Okay? So, don't worry because we are not going to use this formula extensively or even at all. Okay? The purpose of this is really just to compare and contrast our binomial distribution, which I think is more important for us than this, to this Poisson distribution. So, let's look at these bar graphs of two Poisson probability mass distributions. The horizontal axis that you see here, okay, these, represent the number of successes, or K. The vertical axis represent the probability that the random variable X will equal K. Okay, so these are probabilities. These two graphs differ in that a longer time frame is considered here. This is for 6 months, while a shorter time frame is seen in the second, only for 3 months. So this one is the same problem a while ago, the number of deaths attributed to typhoid fever. First, in a span of 6 months. Second, in a span of 3 months. Take note that the occurrence of success, or K, is always skewed towards the right. So there is this shape wherein the tail is always towards the right. And that's a very important trait of a Poisson probability mass distribution, skewed to the right. Meaning to say, it's very rare to have a success outcome. Okay? So, look where the majority of the number of deaths is. Okay? In the 3-month period, that's in 1, right? This is the mode. 1 death. Okay? And then, in a 6-month period, the mode is here. 2 deaths per smaller time frames. So you notice as our time period increases, let's say if we have 1 year instead of 6 months, notice how the extreme positive skewness reduces to become a mildly positively skewed graph in 6 months. We expect that in a year, this will become even less positively skewed, maybe almost normally distributed. So the question is this: how do we know if a discrete random variable follows a Poisson distribution? So for example, when you do coin tosses for many trials, how do we know that that is a Poisson distribution? Or maybe that's not a Poisson distribution. It's actually a binomial distribution. Okay? Fortunately, there's a way to do that. And we simply have to see the relationship between the expected value and the variance of the variable. Okay? So, what do we mean by this? If the expected value is equal to the variance or is approaching, okay, approaching equality with the variance, then your discrete random variable follows a Poisson distribution. Let's recall how we compute for this expected value in binomial distributions. What do? We simply multiply the number of trials times the probability of getting a success. Okay, remember that. And in order to compute for the variance, we simply have to include in the multiplication process the probability of failure. Okay, so remember that. Now, in a Poisson distribution, these two are equal or maybe almost equal. So in this slide, we'll view various scenarios of the binomial probability distribution. So let's go back to that. So like the Poisson distribution, it's actually discrete random variables. So assume an experiment of 10 independent trials with 2 possible outcomes per trial, success or failure. And you are to repeat this experiment of 10 independent trials many, many times. For this first scenario, this is our first scenario, when the probability of success is very low, look at this probability, 0.05 or 5%. It is expected that it is very difficult to come by with a success to all the 10 trials. Now look at this. These are the 10 trials. Okay? It's very difficult to come by with a success. In fact, here, a majority of your repeated experiments resulted in 0 successes out of 10 trials. Look at the mode. It's here on top of 0. Okay? Meaning to say, most of the time, you end up with no successes at all out of 10 trials in your series of experiments. So this graph is what we call, in shape, as extremely positively skewed. Okay, let me just write it that way. Now, for the second scenario, this is our second scenario. Let's assume the probability of success this time is very high, 95%. You might therefore have a majority of your repeated experiments end up with 10 successes out of 10 trials. Now look at this. Most of your results are here on top of 10. 10 out of 10. 10 successes, 10 case out of 10 trials. Okay? That's because the probability of success here is very high. And this graph is just the opposite of the first one. This one is extremely negatively skewed. Okay? So meaning to say its tail is towards the negative side or towards the left. Now, let's liken this third scenario to doing a coin toss. Remember, in a coin toss, the probability of success is equal to the probability of failure, right? 50-50. Okay? So, in this case, your probability of success is 50%. It is therefore expected that for the majority of your repeated experiments, a majority of them will end up with 5 successes out of 10 trials. 1/2 of the time. So that's why our probability mass here is on top of 5 successes out of 10 trials. And the graph follows a bell-shaped curve. Now we go back to our Poisson distribution and see how it resembles. This is our Poisson distribution. This is a binomial distribution with very, very low probability of success. See how it resembles the binomial distribution with very low probabilities of success. And that's really because a Poisson distribution is really just a binomial distribution, okay, where the probability of success per trial is greatly reduced. Very small probability of successes. So, remember how we said that in a Poisson distribution, the expected value is equal or more or less equal to the variance? We can actually test that one here. Okay, let's say the formula for this is n times p. And this should be equal or almost equal to n times p times q. Remember, our n here in this example will be, let's say, we'll have 10 as an n. Okay? It's right there, 10. Okay. Now, for the probability of success, let's just adopt what we have here, 0.05. Okay. And then, let's equate this with the variance, n. We're assuming 10. And of course, our probability of success, we are adopting that from here. And of course, the probability of failure is 1 minus 0.05 or 0.95. Okay? Now, try to multiply this. 10 times 0.05. This is 0.5. Am I correct? 0.5. Okay. And then what about this? Take note, this one is 0.5 times 0.95 is almost a 1. Remember, if you multiply a number to 1 or something that's almost a 1, it's going to be almost, the product will be almost equal to itself. I think this is a 0.4, if I'm not mistaken, 7 something. And 0.5 as an expected value is approaching that of 0.47 as the variance. And therefore, this one is a Poisson distribution.